This videotape deals with multiplication and division of fractions. Up until now, we have just been working with the integers, but our experience tells us that the integers will not be enough for all of our purposes. Consider the following problem. It would take you 3 hours to complete a job working at a uniform rate. How much of the job would you have completed at the end of 2 hours? Of course, the answer is 2/3, a fraction. Okay, let's solve the following equation. 5 times x plus 2, in parentheses, equals 12. 5x plus 10 equals 12. We subtract 10 from both sides, giving us 5x equals 2. Then we divide both sides by 5, giving x equals 2/5. Once again, the answer to our problem is a fraction. So it certainly seems that the integers will not be enough. We will have to include fractions in our work. In a more formal way, let's define the set of rational numbers Okay, the set of rational numbers is the set of all numbers of the form a over b, where a and b are integers, and b is non-zero. We wouldn't want b equal to 0. That would be division by 0. Okay, now from now on, we will be working with the set of rational numbers. Okay? You might notice that the set of rational numbers includes the set of integers that we were working with before. If you have an integer, for example, 6, you could think of that as 6 over 1. So it would follow the definition for rational number. In other words, a quotient of 2 integers, the denominator not 0. And a negative number, for example, -7, could be thought of as -7 over 1. And 0 could be thought of as 0 over 1 or 0 over 2, whatever. So the integers are certainly included in the set of rational numbers. If you were to take a negative integer, for example, -2, and divide it by +3, or if you were to take +2 and divide it by -3, in either case, your answer would be -2/3. Okay? Negative the fraction 2/3 here. Now, you can put the negative sign in the numerator or the denominator or in front. Okay? It's your choice. Most people tend to either put it in the numerator or in front of the fraction. Okay? In our fractions, by the way, over here, a over b, we have a fraction. The top of the fraction is known as the numerator, and the bottom is known as the denominator. Now, I'd like you to recall the basic idea of fractions. That is a way of designating a part of a whole. Let's look at the fraction 1/3. Okay? You may have seen pie diagrams used to describe fractions before. We could take a circle here. Think of it as, say, a pie. And the denominator tells us how many pieces of pie we should divide, how many pieces we should divide the pie up into. In this case, 3. And the numerator tells us how many pieces of pie we are concerned with. In this particular case, only 1 piece out of the 3, 1/3 of the pie, and we can shade off, okay, an area, a section of the pie, okay? And 1/3 represents 1 out of 3 here. Okay, if we were working with the fraction 2/3, the pie is divided into 3 sections, and we are interested in 2 parts. Well, doesn't come out exactly right, but I think you get the idea. Okay. 2/3. 3/3, of course, would be the entire pie. Now, what about 4/3? Here I would need 2 pies since 1 pi only has, let's say 1 pi only has 3/3, for 4/3, I would need here to be 1/3, 2/3, 3/3, that's the entire pi, and 4/3, we'd go into the second pi here. In other words, 4/3 is also 1 and 1/3 pi. This is really 1 plus 1/3. Generally, in algebra, though, we will prefer to write fractions in this improper form rather than in this mixed form of an integer plus a fraction. Now, I would like you to look at the following 4 pi's. The first one I'm going to divide up into halves, 2 equal portions. The second I'm going to divide into quarters. The third into sixths. And the fourth into eighths. In each case, I'm going to shade it in the right side of the pie. I'm asking you to believe that all these 4 pi's, of course, are the same size. You can see, therefore, that, well, we have the same area shaded in each case. And using our idea of fractions, we can represent the same area, the same amount of area in different ways. We can represent it as 1/2. In this case, we have the shaded section being 1/2 of the total pi. In this case, it's 2 out of the 4 pieces of pi. Here it's 3 out of the 6 pieces. And in the last one, we have 1, 2, 3, 4 out of the 8 pieces. All of these fractions are equal to each other. These are equivalent fractions. They represent the same amount of pi. Okay, now let's look at the relationship between the first fraction and the second. 1/2 to 2/4. If you look at the first fraction, if you were to multiply the top of the first fraction by 2 and the bottom by 2, you would wind up with the second fraction, 2/4. To go from the first fraction, 1/2, to the second fraction, 2/4, we multiply the top by 2 and the bottom by 2, the numerator by 2 and the denominator by 2. Now let's look how we can go from the first fraction to the third fraction. To go from 1/2 to 3/6, this can be accomplished by multiplying the numerator of the first fraction by 3 and the denominator also by 3. And to go from the first fraction, 1/2, to the last fraction, 4/8, we could multiply the top of the first fraction by 4 and the bottom by 4. Okay, from this here, it certainly seems that a fraction's value is unchanged if we multiply the top and the bottom by the same non-zero number. And in fact, this is always going to be true, and I'm going to write this down for you. This is the fundamental principle of fractions. Okay, if you take a fraction, a over b, and you multiply the top and the bottom of this fraction, the numerator and the denominator, by the same non-zero number k, okay, you get a fraction which is equal in value to the original fraction. In this case, b is not 0, k is not 0, because we don't divide by 0. In words, we could write it down this way. That is, the value of a fraction is not changed when the numerator and denominator are multiplied by the same non-zero number. Okay, according to this fundamental principle of fractions, 2/3 is equal to 2 times 2, say, over 3 times 2, or 4/6. Okay, these two fractions are equivalent or equal. Okay, to go from 2/3 to 4/6, we multiply the top and the bottom by 2, giving us 4/6. When we do this, when we move from one fraction to another, where the denominator of the second one is larger, we will call this building fractions. We can also use the fundamental principle in reverse. If we start with the fraction 4/6, it is perfectly legitimate to divide numerator and denominator. After all, dividing by a number is the same as multiplying by 1 over the number. Okay? We can divide numerator and denominator by 2, giving us 2/3. Or you could think of it over here. We can write 4 as 2 times 2, 6 is 3 times 2, and cancel out the 2's. Okay, when you work this way, when you go from a fraction to an equivalent fraction having a smaller denominator, we are reducing the fraction. And generally, we try to reduce a fraction to lowest terms. That is, we don't, in the final result, and for example here 2/3, we don't want there to be any factors in common in the numerator and the denominator. See, in 4/6, this was not in lowest terms. Okay, the numerator and denominator had a factor in common, namely 2, so we cancel out the 2's and we wind up with the 2/3. Okay, now in this videotape, we're going to be more concerned with reducing fractions. In the next videotape, which deals with addition and subtraction of fractions, we'll be more interested in building fractions, working in this direction. Let's try some examples in reducing fractions. Okay, reduce each of the following. Reduce each of the following fractions to lowest terms. Okay, let's start simply with 15 over 10. 5 is both a factor of the numerator and the denominator. That is, the numerator here is 3 times 5, and the denominator is 2 times 5. We divide numerator and denominator by 5, or cancel out the 5's to get the resulting answer of 3/2. According to the fundamental principle, 3/2 is the same as 15/10 because we go from this fraction to this fraction by multiplying the top and the bottom by 5. Okay, after you've done this a while, you'll get more used to doing something like this. You'll say, how many 5's in 15? Well, there are 3 5's in 15. How many 5's in 10? 2. And you'll write your answer as 3/2 immediately. Okay, let's try 5/10. Okay, this, of course, is just 5 times 1 over 5 times 2, reducing it to just 1/2. The 5's cancel. Okay, just a word of caution. When you're dealing with something like 5/10, you'd say, how many 5's in 10? That's 2. Don't forget to leave a 1 up here. The answer is 1/2. Don't think of it, say, as 0 over 2 or something like that. We are dividing top and bottom by 5. How many 5's in 5? 1. How many 5's in 10? 2. Final answer, 1/2. Okay, now let's try reducing fractions to lowest terms when we're dealing with fractions that involve variables, not just constants. Okay, let's try this. Minus 9x cubed over 12x. Okay, now it would be great if you could immediately see that these two fractions had a factor in common, namely 3x. And if you were able to say, rewrite this as the numerator as minus 3x squared times 3x, and the denominator as 4 times 3x. This is certainly true. You'd have minus 9x cubed on top and, of course, 12x on the bottom. If you can immediately see the factor in common, fine. You can then divide numerator and denominator by 3x. We're assuming, of course, x is not 0. The 3x's cancel, leaving you with a final answer of minus 3x squared over 4. Okay, if you cannot see this automatically, okay, there are other ways of handling the problem. Okay, one thing you could do would be to actually factor the numerator and the denominator, okay, and make this minus 9 minus 3 times 3, x cubed is x times x times x. And the denominator 12, okay, you could write that as 4 times 3 or 2 times 2 times 3. This will be enough, though, for our purposes. Okay, we have still minus 9x cubed on top, 12x on the bottom. Then it becomes very obvious that the 3x is in common on the top and the bottom. And, of course, we can cancel the 3's, cancel the x's, and finish up with minus 3x squared over 4. Okay, I'm not recommending this method. It would be nice if everybody could do it this way. Okay, but as a last resort, if you can't do it all in your head, you can write it down this way. Hopefully, though, we'll all get to the point where we would work it out something like this. We'd say, how many 3's in 9? Well, that's 3. How many 3's in 12? That's 4. Or I left out the x, okay. How many 3's in 12? That's 4. How many x's in divide the bottom by x? That's 1. Divide the top, x cubed by x, giving you x squared. And once again, we're left with minus 3x squared over 4. Okay, we'll be doing a lot of problems using this idea. First, we took the 3 out of the 9 and the 12, and then we divided top and bottom by x, giving you x squared over 1, and that's your final answer. Of course, you get the same answer all ways. Let me remind you how you multiplied fractions, okay, when you were working in arithmetic. This is the rule for multiplying fractions. And then we can get some more sophisticated problems down. Okay, if you want to multiply two fractions, say a over b times c over d, okay, the way that we do this is to multiply the numerators, a times c, and divide by the product of the denominators. A over b times c over d is AC over BD. Of course, we're assuming here that B and D are not 0. Otherwise, this wouldn't make any sense. Okay, we're going to try a simple problem using this, and then we're going to try some problems where we combine the rule for multiplying fractions with what we already know about reducing fractions. Okay. Let's start with arithmetic. 2 over 2/5 times 3/10. We want to multiply two fractions. Okay, we can multiply the tops and get 6 and divide by the product of the denominators, 6 over 50. Okay, 2 times 3, that gives you 6. The product of the denominators is 50. This is 6 over 50. Of course, this fraction is not in lowest terms, and we can reduce it. What we can do here is to realize that 2 is a factor both in the top and in the bottom. The top is really 3 times 2. The bottom is 25 times 2. And of course, we can cancel out the 2's, giving you a final answer of 3 over 25. Okay, now let's go back to the same problem here. It would have been a little easier if we did the canceling out before we did the multiplication. Whereas we could say how many 2's in 2, that's 1, how many 2's in 10, that's 5, and then proceeded to multiply the numerators. 1 times 3 gives you 3. Multiply the denominators. 5 times 5 is 25. Okay, it doesn't matter if you do the canceling out at the end or if you do it before you start. Sometimes, though, usually it's a little easier to do the canceling out first. Now, it doesn't matter if the factors that you want to cancel are directly underneath each other, or if, in this case, for example, the 2 and the 10 were not on top of each other. It's perfectly okay. After all, what we're going to do eventually is just multiply the tops, multiply the bottoms, and put the top over the bottom. So it doesn't really matter. Any factor in the top can cancel out any factor in the bottom. Okay, it doesn't have to be directly underneath it. Let's try another problem. Okay, 4/9 times minus 5/12. Okay, this is a multiplication problem, right? It's this. Just to make sure you all understand that, I can write it with the dot for multiplication, or of course I can also use the parentheses. Okay, now you can factor out, you can cancel out the 4's first, or you can do it the other way, where you multiply the tops and divide by the product of the bottoms. Let's try it both ways. Okay, the longer way is to say 4 times minus 5 gives you minus 20. 9 times 12, that's 108. This is not in lowest terms. Okay, we see that 2 is a factor both of the top and the bottom. Turns out, though, you can really get by with 4. 4 divides 20 and also 108 with no remainder. Whereas the top is really minus 5 times 4, and the bottom is 27 times 4. At this point, we can cancel the 4's, giving a final answer of minus 5 over 27. Okay, let's try this problem where we reduce before we do the multiplication. Okay, it's a little easier if you first say, okay, 4/9 times minus 5/12. Okay, dividing the numerator here by 4. 4 divided by 4 gives you 1. 12 divided by 4 gives you 3. And then it's 1 times minus 5 for minus 5. 9 times 3 for 27. You immediately get the answer here in lowest terms. Okay, so I certainly recommend this method. Okay, you can start out, if you're a little unsure of yourself this way, but hopefully we'll get to the point where we can reduce first. Okay, let's try some more complicated problems. 18x cubed over 9a squared times 4a squared over 6x. All right, we have a choice here. We could put the 9 into the 18 or the 6 into the 18. It doesn't really matter. You'll get the same answer either way. Okay, how many 6's in 6? 1. How many 6's in 18? 3. Then you can say how many 3's in 3? 1. How many 3's in 9? 3. Okay, then you can divide a squared by a squared, getting 1, and also here, a squared by a squared, giving you 1. Okay, we see an x cubed and an x. Okay, dividing top and the bottom by x, dividing x by x, we get 1. Dividing x cubed by x, we get x squared, giving us a final answer of 4x squared, right? On the top here we have 1 times x squared times 4. That's 4x squared. On the bottom, 3 times 1 times 1 times 1. 4x squared over 3. Okay, remember, if this is too much for you, you could factor the top and the bottom and do your cancellation that way. Now let me give you the rule for division. Okay, we want to divide two fractions. Rule for division. Division of fractions. A over B divided by C over D. The rule says if you want to divide two fractions, what you do is you invert the divisor and multiply. Instead of A over B divided by C over D, we have A over B times D over C. Of course, we're assuming here that B, C, and D are all non-zero. B, C, and D non-zero. You can't have 0 in any of the denominators. Okay, A over B divided by C over D. To divide two fractions, you invert the divisor and multiply. Okay, let me justify this rule for you. This is the fraction A over B divided by the fraction C over D. Now, the fundamental principle of fractions says that we can always multiply the top and the bottom of any fraction by the same non-zero number. Okay, I choose to multiply the top and the bottom of this fraction by D over C. D over C, of course, is not 0. If you remember, B, C, and D are all non-zero. Okay, so D over C is not 0. We can multiply the top and the bottom of this fraction by D over C, and we should get an equivalent fraction. Now, look what happens here. The C's cancel, the D's cancel, and all we're left in the denominator with is 1. So what we have, this is just going to have a value of 1. This is AD over BC all over 1, which of course is just AD over BC. Right? If you have 5 over 1, that's the same as 5. Okay, so in doing this, we're left with 1 in the denominator, and the top A over B times D over C, or AD over BC. And this is exactly what I wrote over here. To divide two fractions, you invert the divisor and multiply. This gives you just AD over BC. So to multiply two fractions, you multiply the tops and divide by the product of the bottoms. Okay, to divide, first you invert and then you multiply. Okay, invert and multiply. Okay, so all the division problems are going to reduce to multiplication problems. Okay, let's try some problems here. Minus 3x over 4y divided by 12xy over 5. Okay, we want to divide these two fractions, so what we do is we invert the second fraction here and we multiply. Okay, let's see. 3 and 12 have a factor in common. We can divide the top by 3 and get 1, and this 12 by 3 and get 4. We can divide top and bottom by x, so the x's will cancel. That seems to be as far as we can go. On the top, we have minus 1 times 5 minus 5. On the bottom, 4y times 4y for 16y squared. Okay, let's try another problem. If you want, you can turn the videotape machine off after you copy the problem and work it out on your own, and then turn it back on to see how you've done. 12x over 15ab squared divided by 8x over 9a squared b. Okay, we're going to do this division by inverting and multiplying, so we'll have multiplication by 9a squared b over 8x. All right, now, let's see what's in common here. We have, well, 8 and 12 have a factor in common, 4. So we can divide the 8 by 4, giving you 2. Divide the 12 by 4, giving 3. Okay, then I see an x in common here and here. We can divide top and bottom by x, leaving you just 1, of course, there in top and bottom. Let's look. 9 and 15 have 3 in common. How many 3's in 15? 5. How many 3's in 9? 3. Now let's look at the a's and the b. Okay, dividing top and bottom by a, you divide a by a, you get 1. Divide a squared by a, you just get a. And the b's, dividing top and bottom by b, dividing the top by b, we just get 1 here. And dividing b squared by b, we're left with a b. Okay, let's see what we have here. We have 3 times a, 9a on the top. On the bottom, 5 times b times 2, that's 10b for an answer to this problem. Okay, before we end this videotape, I just want to mention an important idea, the idea of the reciprocal of a number. Okay, the reciprocal of a non-zero number a is defined to be 1 over a. Okay, if a is non-zero, the reciprocal of a is 1 over a. Let's try some examples. The reciprocal of 3 is 1 over 3. Okay, the reciprocal of 3/4 is 1 over 3/4. Okay, now let's look at 1 over 3/4. Okay, that's division by a fraction. Well, we know how to handle that. Okay, 1 over 3/4, instead of 1 divided by 3/4, we can make it 1 times 4/3. We invert and multiply. 1 divided by 3/4 is 1 times 4/3. We invert and multiply. That gives us 4/3. So the reciprocal of 3/4 is 4/3. And in general, the reciprocal of a over b is b over a, assuming, of course, a and b are not 0. And that brings us to the end of this videotape.